Assalamualaikum and a very good day to our lecturer, Madam Saliha binti Muhammad Sadeh. I'm IQMAL ZIKRY and my friend Muhammad AIMAN will present about the lab 3 resonance for this subject, Advanced Electrical Circuit. So this is our lab. Okay, this is the equipment or components that we need. Oscilloscope, function generator, multimeter, resistor 50 ohm, capacitor 0.33 microfarad, inductor 3 millihenry. So I read the synopsis or theory about the lab. Resonance is a condition in an RLC circuit in which capacitance and inductive reactance are equal in magnitude, thereby resulting in purely resistive dependence. So there are two figures here, figure 1 and figure 2. Figure 1 is the normal RLC circuit and the other one is just add on the R coil or resistor coil. So the first procedure, we need to do some calculation based on the figures given. So we need to find the resonant frequency, half power frequency, F1 and F2, bandwidth, F2 minus F1, quality factor, and dependence during resonance. So this is our calculation that we did. The R coil is given 8.4 ohm. And second one is we need to find the resonant frequency. Resonant frequency is equals to omega naught over 2 pi. So omega naught is equals to 1 over L. Set LC, then we just add on the inductance and capacitance value. So we'll get the value 5.058 kilohertz. And then 2B, we need to find the half frequency. So we need to find omega 1 and omega 2. Okay. The formula is negative for omega 1. The formula is negative R over 2L plus Z R over 2L square plus 1 over LC. So we just add on the values given based on the circuit. Then we'll get the value. F1 is equals to omega 1 over 2 pi, while F2 is equal to omega 2 over 2 pi. Then you get both value, which is 4.475 kilohertz, and the other one 5.717 kilohertz. Okay. Next, we need to find the bandwidth. The bandwidth is equals to F2 minus F1, which is we just get the value just now, 5.717 kilohertz minus 4.475 kilohertz. So we just minus, we'll get the bandwidth value. And then quality factor is equals to resonance frequency over bandwidth. So we just insert the value in the formula, then we got the answer 4.072 kilohertz. Okay, the impedance during resonance is equals to R coil, R coil, not R coil, but total R, which is R 15 ohm plus R coil. So we get 23.4 ohm. Then this is using the multi-sim. So I'll give AIMAN to present and hand on to AIMAN to present.
Thank you, IQMAL, for your explanation. Alright, for this section, I will explain about how we get the measurement. First of all, we will connect the circuit like the figure 1. We have a we have a coil which is value is 8.4 ohm and R is 15 ohm, inductor 3 millihenry and capacitor is 330 millifarad. Alright, we go to the simulation. For simulation, I will use 1 kHz and the amplitude is 2 Vp. Why we use 2 Vp? Because the instruction said the value of amplitude is must 2 Vp. Right, back to the simulation. Right, we get the graph on the oscilloscope. After that, we take this line to the peak of this and this. After that, we will take the value of this, which is 63.775 millivolt. After we take that value, we put in the VR. That value is the value of the VR. For the next step, we change the value of the frequency, which is 2, 3, 4, 5, 6, 7, 8. Lastly is 10 kilohertz. After we get the value of VR, we must get the value of current. We use the Ohm's law, which is we use the value of R and the value of VR and the R. R is 15 ohm, and to that we will get the value of the current of the R. After that, we will plot the data uh, which we get from the VR. Alright, here we have a value of 1 kilohertz frequency, which is we get current is 4.265 milliampere. And after that, we plot all the value and connect the graph for and get this shape. For the IR max, we find from the value of the 5 kilohertz current. For the IR, we use the formula, which is 0.707 multiplied by IR max. We get the value of 40.837 milliampere, and we line at this line. After that, we cut the line into the down and get the value of F1 and F2. After that, we will get the value of bandwidth, which is F2 minus F1, and we get the value of 2.2 kilohertz. This is the bandwidth what we get from the graph. After that, we find the quantity factor. Quantity factor we get from the FO divided by the bandwidth, where we get the value is 2.273 kHz. Alright, next we go to the question. Compare your result between the theoretical and measurement value of the quality factor Q. What might cause the difference? The theoretical value of the quality factor is lower than measurement value because of the bandwidth value. It because theoretical is made by putting a value into the formula, but measurement is actually figure of the given thing. But for the measurement value, we use oscilloscope, which is known as phase noise. This comprises random shift in the phase of signal. This manifests itself as noise that spread out from the main carrier. As might be expected, this noise is not wanted and therefore needs to be minimized. The oscilloscope design can be tailored to reduce this in the number of ways, the chief of being by increasing the Q quality factor of the oscillator tune circuit. At the end, the conclusion of the lab. Finally, during the cycle of the oscillator, the quantity factor link the maximum or peak energy stored in the circuit the returns to the energy wasted by the resistors, implying that in the ratio the resonance frequency to bandwidth. With the higher the circuit, the smaller smaller of the bandwidth. Alright, that's all for our lab video. Thank you.